the strain on an elastic based. Okay. So this is for the dispersion phenomenon. Okay. If you are interested, you can see the book by graph, page 51. Okay. This is a string. Okay. Vibration. Okay. Anyway. So this is elastic foundation, something. Okay. Yeah. So this is X space, and this is Y diffraction at different time. For example, it is at t times. Okay. The foundation with elastic constant, right? And we define we take an element, right? We take an element with something like this. Okay. So we enlarge this. For this length, the S length, okay, and we define the loading at this. For this is X, okay. So this diffraction will be Yx at time t, okay. Okay. Right. So this is loading. External loading is Q, and Q is actually the Q will be defined positive is upward. If I have a positive diffraction in Y direction, then the spring give me a force downward. So this is minus Ky. For a positive diffraction, the Q force will be downward. Okay, yeah. Right, minus Ky. Yeah. So the internal force will be a T internal force T, but this angle will be theta, and this is a T force is theta. Okay, so they were theta plus d theta due to the increment of the x distance. Okay, this is dx. So this is a x plus dx location. Yeah. All right. So from this equilibrium, in y direction, we have minus t sine theta. T sine theta is downward. Okay, so negative. Minus t sine theta plus t sine theta plus d theta. D theta, you can write the partial c part x dx. Okay, and plus q ds is upward force, and will be equal to the unbalanced force will cause us acceleration. So the mass, rho ds will be the mass with acceleration partial y partial t squared. Okay, so this is our equilibrium equation, dynamic equilibrium. Not equilibrium. Okay, so it's a equation of motion in y direction, right? So this is unbalanced force will cause acceleration motion. Okay, so it's very fundamental, but all the derivation for the governing equation start from here. All right, and for sine theta, you can approximate as partial u, partial y, partial y, right? Partial y, partial x. So sine theta plus partial theta partial x dx will be approximated as a partial y, partial x plus this term variation of rate gradient partial x times the dx. Okay? So this is, we can see the d partial y partial x. Okay, this is the meaning. So put inside here, then you can get, all right. Yeah, so this will be partial y, partial x, and this will be partial y, partial x plus d dx, partial y, partial x dx, okay, plus q, and ds, there's a dx, right? Yeah. If we do not consider large diffraction, just for small diffraction, okay. So for small diffraction, we have this 1, 2, 3 ds approximates dx, right? So equal to dou dx partial y partial t squared, right? So we can cancel the dx term, right? Dx, dx, dx. And this will be cancel each other. It's minus. Okay, so this term with this term cancel. So what I have here, then we get the governing equation is a partial y partial x squared minus or plus here we have a t force, sorry, t here, right? Okay, so this will be minus ky, right? So that will be minus ky divided by t equal to dou over t partial y partial t squared. Okay, so this is my equation, and here I define this value c0 squared as the dou over t, t over dou. So this will be 1 over c0 squared. Okay. So if I have an internal tension T and the vibration on elastic foundation, my governing equation will be plus y plus partial y partial square minus k over t y equal to 1 over c0 partial square y, partial t square. So this equation I'm going to solve. Okay, and this is different from the 1 partial y partial x squared equal to 1 over c0 squared. C0 squared. Right, and partial y partial t squared. The form different, okay? And this equation is for the undistortion wave. It has solution f x plus minus c 0t. Okay. The solution is of the form with this x plus minus ct. And this equation will not. Okay. So the solution of this equation is different. Cannot have this kind of form. Okay. This form will have a wave propagating in x positive and negative direction. X. Okay. So this is undistort path propagation. Okay, undistort. Okay, and this will be, we expect this is some type of pulse distortion. Pulse distortion. Okay. So this is a equation we are going to study. Okay. Yeah. See what kind of characters it will have due to the governing equation change. Okay. And this force depends on the formation you have, right? So it's part of solution. The external loading, the Q, is part of solution. All right. So let's see. We still solve the differential equation. And if we call this equation 3 according to our notes, right? This is equation 4. See my notes, right? Yeah. So now, no. Let's see. Let's see what are the conditions where a solution y equal to a exponential I gamma x minus omega t. Okay, so this is a wave propagated in the positive direction, right? So we want to see if this equation is our solution, what kind of a requirement, the conditions required to satisfy equation 3. right? So this, for this solution of this form, what kind of requirement on gamma and omega, okay, it should have to satisfy this Galvin equation. Certainly, we'll have to put into the equation. So it is equation 5, right? Now, if you have this, so y x will be what? I gamma, right? A E I gamma x minus omega t, right? And y gamma x will be I gamma square A E I gamma x minus omega t. And yt will be I omega, right? Minus I omega. A E I gamma x minus omega t. And ytt be minus I omega square A E I gamma x minus omega t, right? And this will be minus gamma square A E I gamma x minus omega t. And this will be, oh, right. So the positive, right? Omega square A E I gamma x minus omega t. So let's put it into the Galvin equation will be minus gamma square A, right? And minus k over t A, right? And equal to 1 over C0 square. T is omega square A, right? Huh? Right. Yeah. A and times E I gamma x minus omega t equal to 0, right? So this can be write as minus gamma square minus k over t minus minus plus right. So am I doing wrong? Oh. So this minus, right? It's funny, huh? X, right? X is minus, right? So minus here is minus, and here is positive. So if I put on this side, that will be omega square over C0 square A E I gamma x minus omega t equal to 0, right? Oh, right. It's all right. So for non-trivial solution, A cannot be 0, right? So this cannot be 0. If 0 is a 0, set it auto. So we have to force this term become 0. Okay. So this term we have 0 will be have omega something weird. Because my nose here is a plus sign. I don't know why.
那个是不是少一个符号？那个 y 对 t 两次微分。啊。你那个那边是不是里面少一个符号？
哦，这应该是正号。
对对，这样。
正号。
正号后面那个 omega 前面应该要带一个。
No， 正号，因为再一次微分的话是 minus 是正号。
对啊，所以 i omega 平方嘛。
对，甚至就负号，就负了，对，负号，对，那就正号。哦，我跟他对了 ，all right，OK， 这边是正号，笔记是这样对的啊。所以那这个时候 ，so this term should be equal 0, so we have a requirement. Yeah, so we require the omega square equal to C0 square gamma square plus K over T. So this is my requirement about the relation about omega and gamma. We have to satisfy this equation, okay? Or you can write gamma in terms of omega is omega square over C0 square minus K over T. So this is a condition, either one, okay? We have to satisfy. If we have a solution of y equal to A E I gamma x minus omega t. So this is a requirement between the gamma and omega, they have to satisfy. Okay, yeah. If I want a solution of this form, there's a requirement for the two parameters. Yeah. Okay. Okay. If I say I would like to express the solution in another form. Okay. So if this form, I like to express the solution like A E I gamma x minus CT. So I use a gamma and C. C is a kind of a wave speed. Okay. Gamma is a wave number. If I like to this form, see, I will say what kind of condition I need to satisfy. Do the same thing. You have the y x equal to I gamma, right? A E I gamma x minus CT, and y gamma x equal to the I gamma square A E I gamma x minus CT, right?